So good evening. I'm Laurel Traynor, and I'm the director of the McMaster Institute for Music in the Mind. And I'd just like to welcome you all here tonight. I'm sorry about the delay, but we were registering some people for the synesthesia conference, and it took us a little bit longer than we thought. But the good side of that is we're very happy this year that we're doing our annual lecture and concert in association with the American Synesthesia Association, who is having a conference that will take place this weekend. There's more information in your programs if you are interested in attending that. I'd also like to remind you that if you want more information about what we do at the McMaster Institute for Music in the Mind, you can visit our website. That's also on your program. And we're happy to have you come out to any of our events. So tonight I'm very happy that we have John Capone, who's the Dean of Science at McMaster, who will introduce our evening. So, John.
Thank you, Laurel, and good evening, everyone, and welcome to the fourth integrated lecture and concert sponsored by the McMaster Institute for Music and the Mind. I'm delighted that you were able to join us for what promises to be a really remarkable evening. The Institute for Music and the Mind at McMaster is a world leader in the scientific study of music. At McMaster, our researchers are investigating the power of music, the role it plays in human development and human behavior. We have a history of success when it comes to bridging the arts and sciences in both our teaching and research, and the McMaster Institute for Music and the Mind is perhaps our most creative example of bringing the two disciplines together. We are grateful to Laurel Traynor, the Institute's director, for her expertise and passion in creating this research center and in ensuring its growth and sustainability. I would particularly like to welcome tonight the delegates of the 7th Annual Conference of the American Synesthesia Association. This conference is another example of the exciting things that we do here at McMaster in the Faculty of Science and through institutes like the one that we are here to enjoy this evening. This conference was organized by Daphne Maurer in the Department of Psychology, Neuroscience and Behavior, and Daphne will be our speaker tonight in the second half of the program. Tonight we are going to look at music in the context of other senses. Yes, we hear music, but we'll see that music is not just about sound. In the first half of the program, Stephen Brown, an assistant professor in the Department of Psychology, Neuroscience and Behavior, will consider why we have aesthetic responses, that is, why we like some things and dislike other things, and how music fits into this picture. In the second half, Daphne will take us on a journey into the perceptions of people with synesthesia, some of whom literally see colors when they hear music. And as every year, we will be treated to wonderful musical performances. So without further ado, let's start the evening by welcoming Stephen Brown.
Okay, thank you, John. The title for my part of the talk is A Pretty Girl is Like a Melody. This is actually the title of a song by Irving Berlin, composed in 1918. If you saw a film called The Great Ziegfeld, you will have seen this production number of A Pretty Girl is Like a Melody. So before I start my talk, I'd like to hear some music, and I'd like to invite David Haller, tenor, and Cécile Desrosiers, pianist, to perform this beautiful song by Irving Berlin.
I have an ear for music, and I have an eye for a maid. I like a pretty girlie with each pretty tune that's played. They go together like sunny weather goes with the month of May. I've studied girls and music, so I'm qualified to say a pretty girl is like a melody that haunts you night and day. of a haunting refrain. She'll start upon a marathon and run around your brain. You can't escape. She's in your memory by morning, night, and noon. She will leave you and then come back again. A pretty girl is just like a pretty tune. A pretty girl is like a melody that haunts you night and day, just like the strain of a haunting refrain. She'll start upon a marathon and run around your brain. You can't escape. She's in your memory by morning, night, and noon. She will leave you and then come back again. A pretty girl is just like a pretty tune.
Okay, thank you, David and Cecile. Okay, so this talk is about aesthetic preferences, those things we like, those things we dislike, those things that turn us on, those things that repel us. And so I'd like to kind of gauge some of your aesthetic preferences, if you don't mind, just to start this talk. And so I'd like to ask people with a show of hands to indicate which of you think that Stephen Harper, Prime Minister of Canada, is an attractive-looking man. Okay, that was very interesting because very few people raised their hands. Definitely when you see the G8 summit photos, he's definitely one of the better-looking people in the picture, I think. As a total aside to what I'm going to say here, I just want to point out that psychological research shows that men are very evasive when it comes to making judgments about the looks of other men. And so if you give a series of pictures of male and female faces to women, they can rate the men and women with equal ease. But if you show the same group of pictures to men, they can rate the women's faces. But when it comes to rating the men, they say that they can't make the judgment. They're incapable of making the judgment. So anyways, for those men of you in the audience who raised your hands for Stephen Harper, I commend you for your honesty and forthrightness. Not so much for your taste, but definitely for your honesty. Okay, so here's a kind of assessment that occurs in the domain of vision. Let's switch senses. Let me ask you about foods and your sense of taste for foods. So how many people in the audience here have an appreciation for the taste of horseradish? Stephen Harper? Well, many more. And how many people who raised their hand for Stephen Harper have an appreciation for the taste of bitter things? Okay. Anyways, the basic topic here is aesthetic preferences. Now, the term aesthetics goes back to 18th century German philosophy and deals with the experience of the appreciation of great works of art. And so the feeling you feel when you look at a Rembrandt or hear a symphony by Beethoven. And that's all good and fine, but I want to get the point across that we make aesthetic judgments not just about great works of art, but about everything that we perceive in our environment. So when you see people, you make assessments of their faces, their bodies, their wardrobe. You assess the interiors, exteriors of buildings, tastes of foods. And so this is kind of a general thing that we as people do. We make aesthetic judgments of those objects that we come in contact with. Some things we love, some things we find repellent. And definitely a first step in this process, first you have to, in some level, perceive the sensory features. So in order to make an assessment of Stephen Harper, you first have to perceive the shape, the contours, the colors of his face. But that in itself is not sufficient. Beyond that, you have to make what we'll call an appraisal. Make a decision about whether this is appealing, unappealing, good for me, bad for me, and the like. Now, neuroscience research has shown us that a particular part of the brain, called the orbitofrontal cortex, is kind of the key area involved in this process of making aesthetic assessments of objects. The term orbitofrontal comes from the fact that it's located in the front of the brain, here, and the term orbit in anatomy refers to the eye socket. And so this is the part of the brain that sits directly above the eye socket, hence orbitofrontal. And brain imaging studies have shown that this one area responds when people have to make aesthetic judgments of a wide variety of different kinds of stimuli, including whether they make an assessment, whether they like or dislike a piece of music, the taste of foods, smells, whether touches are pleasant or unpleasant, paintings, people's faces, images of food, and even erotic images. The same brain area seems to be activated when people have to make aesthetic judgments across a wide variety of different sensory modalities. And so basically we see a major convergence of the senses in this part of the brain. But it's not just for sensory processing alone, but convergence in the service of making aesthetic appraisals of objects, different kinds of objects in our environment. And so we can ask, what function does this convergence serve biologically? Why do we find this convergence of the senses in the orbitofrontal cortex? And to help answer that question, I'd like to call back our performers, so David Haller, tenor, and Cécile de Rosier, who will sing a song about another pretty girl, Sarah Lee. This is a song by John Kander and Fred Ebb.
It's a song about a pretty girl, but more importantly, it's a song about food. There's a lady living somewhere. Where it is, I do not know. But I long to write and tell her that I love her so. I believe I might do mayhem. Yes, I might destroy myself if I ever found her missing from my grocer's shelf. Sarah Lee, Sarah Lee, your brioche just fractures me. Give me a taste of your cherry Danish. I love my mother, but you can't compare her, not to Sarah Lee. Sarah Lee, there's no H, just Sarah Lee, and that's okay with me, 'cause I'm living in paradise when I'm nibbling apple spice from the kitchens of the one I love, wonderful Sarah Lee. And it thrills me right to my soul when I'm chewing her finger roll. You hear me saying, for goodness sake, there's never been a better banana cake. Cousin Milton works at the Hilton. He caters banquets, and at each affair he'll swear by Sarah Lee. I really know what you mean. Sarah Lee, aren't her brownies obscene? Drop that H, just Sarah and that's okay by me. I love a cheesecake white as pearl. And did I mention that chocolate swirl from the kitchens of the one I love? Wonderful Sarah, beautiful S-A-R-A-L-E-E, Sarah Lee.
So the best biological theory we have about why we find this kind of convergence of the senses in the orbital frontal cortex is this hypothesis that is involved in the appraisal of food quality. And so we appraise food sources with many different sensory systems. For food that's outside the mouth that we perceive at a distance, we use vision, we use smell, and we use touch. So we can tell if a piece of fruit is ripe or spoiled based on its visual appearance, based on the smell, based on the touch. Once food enters the mouth, we have additional senses involved, including the sense of taste, sense of smell, and also the texture, the touch, but the texture of the food inside the mouth. And by the way, what we call flavor is actually a combination of taste and smell. So we think about flavors being just the taste, but actually the flavor is the combined effect of the taste and the smell of the food. And so this kind of hypothesis about food appraisal sort of gives an explanation for why we see a convergence of at least these senses, so vision, smell, taste, and touch, in the orbital frontal cortex, which is all good and fine, but it leads to kind of the paradox that was the opening of this talk, a pretty girl is like a melody. And that's kind of my way of saying that how do we get these other things, like pretty faces and pretty music, how do they make their way into the system supposedly involved in the appraisal of food sources? When it comes to faces, for me, it's not a big leap to get from food to faces, because we know from neuroscience that there seems to be a connection between the visual system and this orbital frontal cortex. So in some basic way, pretty faces may just be an extension, an extrapolation of the visual appearance of food sources. But how about music? Can we explain our appreciation of music as some kind of extension of our appraisal of food sources? And as typical for people who think about the biological basis of music, music is always a big mystery. And so I present you these questions. Why do people have such a strong appetite for music? In what way does music nourish people? Okay, these are big questions for which we don't have any simple answers. A very well-known linguist called Steven Pinker has proclaimed that music is nothing more than auditory cheesecake. And like real cheesecake, it's the kind of thing that we crave, but serves no particular survival value. So we crave cheesecake, but it doesn't really provide any nutrition. It increases our cholesterol, makes us overweight, and the like. And so for him, music is this kind of very attractive thing that we crave, but it doesn't in any way support our survival, doesn't nourish us in any significant way. Now, thinkers a bit less cynical than Steven Pinker have proposed other kinds of biological scenarios for how music may have evolved. And I'll present the two major alternatives to the auditory cheesecake, which definitely predated Steven Pinker. The first goes back to Charles Darwin and his contention that birdsong, at least in many species, is a form of courtship display. And so he talked about this notion of sexual selection. So in many species of birds, not all, only the males sing. The females can respond to it, but they don't sing themselves. And so Darwin thought this is a good example of a sexual display, a kind of courtship display used for attracting mates. Also a sign of kind of the health of the bird, because if the bird were not healthy, it wouldn't be able to sing these songs for hours and hours. So Darwin proposed that music, like birdsong, is a kind of aesthetic display for the purpose of attracting mates. Another view, using a different animal analogy, is that music is, instead of being like a courtship display, is more like a territorial display. So wolf packs howl every day, and they do that to mark their territories acoustically, but also to create a sense of cohesion among members who are in the group versus those who are outside the group. And so, by analogy to this, the music would be sort of a territorial display used by groups to mark their territories, but also establish relationships, cohesion within the group. So of these two hypotheses, as far as is music more involved with appraisal of mates or appraisal of social groups, I myself tend to lean on the side of groups. And I'll give you kind of my reasons for why I think that music is more about social groups than about courtship. First of all, we know from a century of ethnomusicology research that music is mainly created in groups. Our kind of society is a bit of an aberration, so here we have musicians performing in front of hundreds of kind of passive listeners. That's not the typical situation in a tribal culture or a village culture where pretty much all the people in the group are active in aspects of performance together. So less of a separation between musicians and audience or non-musicians and musicians. Pretty much everyone gets in the act of making music. In addition, music has sort of two intrinsic features that make it seem like it's very well designed for being a group coordination device. One is the fact that all people are able to, as we'll say, keep the beat. They're able to synchronize their movements to a timekeeper like a drum. And so we have this capacity for what we could call beat-based coordination. This is important not just for musicians to coordinate with each other, but for dancers to synchronize to the beat of music. In addition, humans are the most complex singers of all animals in nature. And so we have a lot of different styles of blending that we call polyphony. So in polyphony, people sing different parts, but coordinate their different parts to create a unified sound, and that's called polyphony. And there are many different types of polyphony that are used in world music cultures, and so we're kind of the star when it comes to creating all these different kinds of very complex polyphonic musical blends. Okay, so just to give some musical meat to this, I want to play two musical examples that kind of demonstrate in part the groupishness of music, also the importance of the beat and of creating these complex textures that we call polyphonic blends. The first one comes from Tanzania, and it's from a tribe or a people called the Wagogo who live in the center of Tanzania. And I'll play like about 90 seconds from one of their songs. What you're not going to be able to see here is actually the dance element. You're going to hear instruments, you're going to hear polyphonic singing. What you're missing actually is how all this is being coordinated with body movement and with dance. About 8 years ago, I spent a month traveling through Tanzania. And in addition to doing the usual things like going to Kilimanjaro and Serengeti, I went to Dodoma, which is where this particular ethnic group is localized, because I really wanted to buy instruments. I'd known the Wagogo music for a long time, and I wanted to purchase their instruments. And that day was very unforgettable because the instrument place was kind of a kiosk just sitting on the street. And so I went there was just one guy there and a bunch of instruments hanging. And so when I arrived, it was just me and the vendor. By the time I left, half an hour later, there were 100 people. there in addition to me. And they were really intrigued why this Umzungu, this white guy, was there buying their instruments. And so really it was first just me and this guy, and then people just started flocking and flocking as they saw that I was there to buy their instruments. And a really fun day. The second example comes from the island of Corsica, which is an island just south of France. And again, they have a very beautiful form of polyphonic singing, which is well known. And so let me just play a short example of polyphony from Corsica. Okay, so I've talked about this kind of convergence of the senses in relation to aesthetic processing, but we also see a very important confluence of the senses with regard to music and dance. And so we see this combination not just of hearing, but vision, our kinesthetic, our joint sense. If you're dancing with people, you have physical contact with them. And of course, we have movement, which is beyond just pure sensation. And so again, music, we see this convergence of the senses with music. So to kind of bring the point home, I'd argue that music, at its origins, is related to the appraisal of the quality of social groups, how coordinated they are, how much you can identify with that particular group. And so I would say that our appetite for music ultimately may be about the pleasure of communion. Okay, so I've talked in this half of the event about this convergence of the senses for aesthetic appraisal, also for music and dance. And now we're going to take this kind of to the next level, the next step, and talk about another kind of convergence that we call synesthesia. And to kind of bring us in that direction, we're going to hear a piece of music by the French composer Olivier Messiaen, who himself was a synesthete. So he saw colors when he heard pitches and heard chords. And so we're going to hear a piece of his, the Theme and Variations, one of his early works, performed here by Mark Whale on the violin and Brett Kingsbury on the piano.
I'm Daphne Maurer, and you just heard the link between the two parts of this evening. You heard a piece of music by Olivier Messiaen, who was a synesthete. He had a form of synesthesia in which he heard pitches and timbres in color. Synesthesia comes from the Greek roots syn for union and aesthesia for sensation. So in individuals with synesthesia, stimulation of one sense, like hearing something with the ears, evokes an extra perception, such as seeing, perceiving something with the eyes, hearing a pitch, perceiving a color, an extra sense, an extra dimension of the stimulus. It comes in many different forms. I think the current estimate is that there may be 54 types of synesthesia. So for a synesthete, sound, a very specific sound, let's say C sharp on the trumpet, may elicit a specific color, the perception of red. Or it might elicit, for another synesthete, a specific shape, like a jagged shape. And for still another synesthete, a highly specific taste, like the taste of oranges. But not any old orange, that taste of an orange that is just not quite ripe. For another synesthete, that sound of C sharp on a trumpet might be blue, or a swirly shape, or the taste of mint. For other individuals with synesthesia, the elicitor is a digit or letter of the alphabet printed in black, a 2, a W, an S, a P, a 4, and an H, and evokes an extra dimension of vision. So it's perceived as coming with a color. 2's For a particular synesthete, 2s and W's might be red, S's, 5s and P's might be blue, 4s and H's might be green. You can get some feeling of what it's like to have synesthesia, and I'm not one of the people who's blessed with it myself, from this quotation that accompanies the painting by Carol Steen, who's both a visual artist and a synesthete. The painting is called Runs Off in Front Gold, and details from it are printed on the cover of your program. This is what Carol says. While I listened to Santano's version of a song called Aduma, I played this song over and over again as I painted the moving colors. So she's listening to a song, she's seeing colors, she's seeing shapes, and they're moving. It's highly dynamic, and they inspired this painting. Now, I've conveyed to you, I hope, that synesthesia is very idiosyncratic. The form of it differs between individuals, particular mappings differ between individuals, but something that's common for everybody with synesthesia, it's automatic. They aren't sitting there and thinking about what's the best color to go with 5, what's the best color to go with a C sharp on a trumpet. It just comes. It's automatic. They report having had this extra rich perception all their lives. And importantly, their mappings, although idiosyncratic and highly special, are consistent over time. So if Carol Steen played that song today, she would see the same moving colors that she saw when she originally made that painting. The incidence of synesthesia, our best current estimate is it probably occurs in 4 to 5% of the adult population. The incidence is probably a little higher here tonight because this is the opening event of the American Synesthesia Association conference, and many synesthetes choose to come to that conference to learn more about their own perceptions. It's just as common in men as in women. And among those who have synesthesia, about 10 to 20% connect music to color. They have colored hearing. Now, colored hearing, or colored music synesthesia, turns out to have been very common in musicians and composers, or to be very common in musicians and composers. Liszt, whom we'll be hearing at the end of tonight's program, was a synesthete. He was also a conductor, and when he conducted the orchestra, he would say things like, "Oh, please, gentlemen, a little bluer, if you please. This tone type requires it." So he's telling the musicians how to play the music with color terms, which at first they thought was quite strange, but they came to understand this language as they worked with him. It's not just classical musicians, it's also common in jazz musicians. An example is Duke Ellington, who said, if Harry Carney is playing D, it's dark blue burlap. That's Harry Carney, who was playing the low baritone sax, so that low baritone pitch was dark blue burlap. Whereas if Johnny Hodges is playing, and this is on the alto sax, so it's a higher pitch, the G becomes light blue satin. And it's even common in contemporary musicians. Here are some examples that my students found for me, and they tell me that you are looking at pictures of Stevie Wonder, of John Bon Jovi, the rock guitarist. All right, you know, doesn't matter that I don't. I already told you that. And Pharrell Williams, the hip-hop artist and producer, whose latest album was called Seeing Sounds. So I've told you what synesthesia is. I've told you that probably 90-95% of you sitting here tonight don't have it. and that it's very common in musicians. And I'm sure that 90 to 95% of you who don't have it are sitting there thinking, what is this? Is this real? Is this imagination? Well, the work of scientists in the last decade has proved that it is a real phenomenon. And the scientists who did that work are mostly sitting here in the audience tonight. Let me give you some examples of their findings. One thing they found is that synesthesia works just like everyday typical perception. So, if a synesthete tells us that when I look at a 2, I perceive red, that black 2 behaves for that synesthete just like showing you all a red 2. I'll give you 2 examples. One is from what's called the Stroop effect. Now, this is the classic way psychologists for decades have tested for the Stroop effect. So we're going to do this all together. Your job is to ignore the words and just report the color of the ink. Okay, so let's start in the upper left corner. We're going to go blue, everybody. Blue, orange, red, green, purple, oops. Okay, it's hard. You were slow. Why were you slow? You were slow because your brain is automatically reading the words. It's automatically processing the meaning of the words. You can't help but get interference from the meaning of the words. It's preventing you from doing the task. Now let's do it with colored digits, and anybody who has colored digits in the seat should not participate this time. Let's try it now. Ignore the digits, read the color of the ink. Red, green, red, green, red, green, green, red. It's a cinch. No Stroop interference. But if you're one of the people sitting here who has colored graphemes, this one was not easy. Let's suppose that for a particular synesthete, 2s induce red and 5s induce green. I set this up so that for that synesthete, the ones on the left are going to be easy because they're in the right colors. There's going to be no interference from the synesthetic percepts. And I set it up so the ones on the right are going to be hard because I put them in the opponent incompatible color. And so for synesthetes who tell us they have colored digits, exactly that Stroop effect happens with these colored digits. So they quickly read the ones on the left, they don't make errors, and they very slowly read the ones on the right, making many errors, and actually complaining about being in the experiment because it's hard to do. The second example I'll give you from the scientists' work is a phenomenon called pop-out. So anybody who hasn't seen this before and who is not a synesthete with colored digits, find the shape. Who's found it? Raise your hand as soon as you find it. Okay, some of you are getting it, but it's not easy. That same task is a cinch for synesthetes for whom 2s and 5s cause perceptions of different colors. This is our best guess of what it may look like to such a synesthete. It pops out, they can see that triangular shape much faster than individuals who don't have colored digit synesthesia. So, Stroop effects and pop-outs tell us that synesthesia is working just like typical everyday perception. We're seeing the same patterns of interference and facilitation in the Stroop effect and in pop-out. Scientists in this room have also shown us that synesthesia uses the same brain areas we use in typical everyday perception. And they found this out using a technique called functional magnetic resonance imaging, or fMRI. fMRI records changes in the flow of oxygenated blood. So the logic of how it works is that when neurons are active, they demand more oxygenated blood. There will be more blood flow to those areas of the brain. The MRI scanner picks up that change, and those areas that light up are the areas that are active because they needed more oxygenated blood. Now, before I tell you about the synesthesia results, I need to tell you something about the brain of every adult in this room. We have what are called sensory cortices. These are areas that are specialized for one of our senses. So if you look at this brain, the front's over on the left. We're looking at a side view. There's an area at the back here called the occipital lobe or the visual cortex, and neurons in that area respond only to visual signals, only to information coming in through the eyes. Down at the bottom, you'll see a label that says auditory cortex, and there's a line pointing to the middle of the brain. Neurons in that area respond only to sound, only to information that's coming in through the ears. And at the top, I've got somatosensory cortex pointing to that strip right underneath it. This is the area where neurons respond to tactile information, to touch. So our brains have specialized areas for individual senses, and then at higher areas, the information gets put together because, of course, we see an integrated world involving all our senses at the same time. Now let's look at the fMRI results for individuals with colored hearing synesthesia. When they are in the scan or listening to sound, there's activation in the cortical pathways active in everybody for the processing of sound. So in the auditory cortex, information is coming in through the ear, going to the auditory cortex in the middle of the brain. No surprises. But at the same time, there's activation in cortical pathways in visual areas that are involved in the processing of color. So at the same time, while people with colored hearing are lying in the scanner, there's activity in the visual cortex at the back of the brain, in particular an area that we know is involved in the processing of color. So, when a synesthete looks at something or listens to something and says, "I perceive color," it's real. They are perceiving color because that color interacts with real-world color, with interference and facilitation, and it uses the same brain areas we use to process color in our everyday lives. So let's continue by listening to another piece of music by Messiaen, who was very explicit in his writings about his synesthesia. Here's a quote from his writings. "I too see colors, if only in my mind, colors corresponding to sound. It's all very mobile. You've got to feel sound moving." Now we're going to listen to a piece played by Brett Kingsbury on the piano called La Colombe. Messiaen was very explicit that he used his synesthesia, his colored hearing, in composing. He said in one of his books, "I sense these colors in an extremely vivid manner. I try to incorporate this in my work." So when he was composing that piece we just heard, he's partly playing with his colors as well as his sense of musical properties. How does his use of his synesthetic color affect how those of us who don't have synesthesia hear that work? Well, to answer that question, we have to make a detour through development. So we're going to go back to infancy, but I need you to remember that what I told you is going on in the brain of someone like Messiaen with colored hearing synesthesia. When that individual listens to sound, there's activity in the auditory cortex that responds to sound, but there's also activity at the back of the brain in a visual area that's specialized for color. There's a connection just like that that seems to be operating in infancy. So in infant monkeys, anatomical tracing studies have shown that there's a direct connection between the auditory cortex in the middle of the brain and the visual cortex, in particular V4 that responds to color, that's present there in infant monkeys, but that gets pruned away before adulthood. The same kind of connection between hearing and vision appears to exist in human infants and young children. People haven't done anatomical tracing studies, haven't sliced open the brains of babies, but they have been able to get this information using EEG recordings, electroencephalography. So here's a baby wearing a head full of electrodes in order to record changes in electrical signals reaching the scalp. Here's the adult wired up for the same study. When Helen Neville used this technique, what she discovered is that when listeners are presented with sound, in adults, there's a change in activity in areas corresponding to the auditory cortex, and nothing happens in other cortical areas. That's as it should be. I told you the auditory cortex is specialized for sound, and the visual area, the somatosensory area, don't respond to sound. No surprises. But then she did the same study with babies. When babies listened to the sound, there was activity over the auditory cortex, but every bit as much activity over the visual cortex. And gradually the visual activity diminished over years as the baby started to grow up, suggesting that in early childhood, just as in synesthetes, there are extra functional connections among sensory cortical areas. Now, in typical development, most of those extra connections get pruned away, and here's how we think it works. The baby is born, hasn't had any visual experience because the baby's asleep. The visual cortex at that point will respond to vision, to hearing, or to touch. But the baby starts to get visual experience, starts to feed visual information into the visual cortex that is strong, that's fast, that is coherent, that reinforces the visual connections, and as a result, the connections to hearing and touch get pruned away. And our best evidence for this comes from babies who don't get visual experience because they're born blind. So in the baby who grows up blind, there is no functional input coming through the eyes. But of course, the baby can hear, the baby can feel touch. So information from the ears and the skin does get fed to the visual cortex. And when these babies grow up, what should be the visual cortex turns out to be specialized for hearing and for touch. And that's what tells us in the child who can see. It's the experience of seeing that's tuning up the visual cortex for vision. It's the experience of hearing that's tuning up the auditory cortex for hearing. It's the experience of being touched that's tuning up the somatosensory cortex for touch. And it's doing that by pruning away those extra connections. So let's move on and hear a piece of music by another composer, Amy Beach, an American composer, who also had colored hearing synesthesia. So our best guess is, as with Messiaen, some of those extra connections present in infancy didn't pruned away. They persisted into adulthood, underlying colored hearing synesthesia. Amy Beach, when she was a child, is reported by her mother to say on one day of the week, "Oh, mother, please play the purple music." And another time she would say, "Oh, mother, please play the green music." Throughout her life, she reported the colors associated to the notes that I have on the screen. She did this when she was a child. She did this when she was an adult. So this is her form of colored hearing synesthesia. And let's hear her work called Andante Espressivo, played by David Gary on the flute and Cécile Desrossiers on the piano. two balls that should be moving up and down the screen if I had animated this. One is lighter and one is darker. One hits the surface and goes bing, and the other hits the surface and goes bong. Which one is going bing? How many people think it's the ball on the right? How many people think it's the ball on the left that goes bing? So almost everybody here, everybody who raised their hand, thinks that the higher pitch is coming from the lighter ball. We did exactly that same study with toddlers. We asked them which ball is making the sound. We presented from the central speaker a higher pitch and a lower pitch, and 100% of the toddlers told us that the higher pitch was coming from the lighter ball and the lower pitch was coming from the darker ball. So in this audience that contains both synesthetes and non-synesthetes, there seems to be an agreement that lighter goes with higher pitch. On the right side of this slide, I show some data from Jamie Ward. And where's Brett? Brett's actually this is what now these are synesthetes with colored hearing. This is the stimulus that was presented to them, and they were asked to choose the best color and lightness for each of these notes. Yep. Okay, these are the results for one synesthete. Thank you, Brett, with colored hearing. So it's the color that goes with each of the pitch from two different runs, highly specific color. But you'll notice that as you go from left to right, from lower pitch to higher pitch, the colors are getting lighter. And that was a finding across all the synesthetes tested and all the non-synesthetes tested. These are the group data from that study. The lightness of the color chosen is a function of the pitch. Higher pitches go with lighter, whether you're a synesthete or a non-synesthete. And this relationship between pitch and lightness unconsciously affects the perception of all of us. A really beautiful example of that comes from a study done by Larry Marks, who's also in the audience tonight, and I'm trying to depict this with visual images. So your job in this experiment is to look at the light on the screen each time. It can be lighter, it can be darker, and you push a button every time it's the lighter one. And you push the button just as fast as you can, but don't make any errors. So that's your job. It's a really fairly boring experiment. Every time it's the lighter one, push the button. Don't push the button when it's the darker one. Larry Mark's trick was that there was a distracting sound in the room. And sometimes the distracting sound had a higher pitch. Sometimes the distracting sound had a lower pitch. Subjects were told it was irrelevant, just to ignore it, but they couldn't. When the higher pitch came on a trial with the brighter light, they were faster. They made fewer errors. When the lower pitch came on in a trial with a brighter light, the wrong mapping, they were slower. They made more errors. So this relationship we seem to understand between pitch and lightness has an unconscious influence on how we perceive light, and then in another experiment he shows it in the reverse direction, that a distracting light in the room affects the accuracy with which you perceive pitch. So what I've told you is that I wasn't quite right in what I said in the middle part of this talk. Because in the middle part of this talk, I told you that we have sensory cortices that are completely specialized for just one sense, that they start off really interconnected, and that during development, experience prunes away those extra connections, so the visual area is very isolated during vision, the auditory area is very isolated during hearing. But in this last part, I've told you that's not quite true. That in all of us, some of those connections between the sensory cortices remain, linking vision to hearing, hearing to touch, etc. So now I've changed this slide. Instead of crossing out hearing and touch, they're now dotted lines. So some connections, like those in synesthetes, exist in the brains of all of us, affect our perception. How do they affect our viewing of synesthetic visual art, or listening to the music of a synesthetic composer? Whoops. Okay. So, do these remaining connections make synesthetic art compelling to us? Now, I have a question mark there, because we really don't know. We're thinking about this question. It's just beginning to be investigated empirically. And I'm going to tell you about one of the first pieces of empirical data that come from the lab of Jamie Ward, and his slides will not work on my computer, so we are going to switch computers. So the way the experiment worked is that he had 5 individuals with colored hearing synesthesia come into the lab. He played a whole bunch of different pitches, different chords, different runs of notes on various instruments. And for each one, he asked each of the synesthetes to describe what they saw, and then had a very skilled visual animator, Samantha Moore, I believe was her name, simulate what the synesthete was describing and show it to them until she got it right. Okay? So now we have some images of what the visual percepts, what the colors, the shapes, the movement is like for individuals with colored hearing. I'm about to show them to you. So then what Jamie Ward did was bring non-synesthetes into the lab, show them these animations as they originally were described by the synesthetes. Okay. And then in ways he had transformed them, in ways he had distorted them. And the question is, do you like the original, or do you like the one that's changed? Is it more appealing? Do you like it more? Does it have more, give you more aesthetic pleasure in the way it's mapped by the synesthete with colored hearing? Or it makes no difference to you whether it's the original or the one that's transformed. Okay, the first one, you'll hear the sound. One of these is as the person with colored hearing described it, and the other one is with the color altered. And so I'm going to show it, and then we're going to have a vote. Which one's better? Which one's more appealing? Okay. Show it to you again. How many people like better the one on the left? How many people like better the one on the right? Okay. There are some votes for each. There were more left choices than right choices. Show you another one. One of these is as a synesthete described what he or she was seeing in response to the sound. The other one, the orientation and direction of movement has been altered. Okay, so let's look at these. How many people like better the one on the left? How many people like better the one on the right? This one's overwhelmingly left, although there are a few people who prefer the one on the right. Okay, want to switch back? The data in this room are very similar to the data that Jamie Ward collected in the lab, with many, many, many more trials than I just showed you. The ones on the left were the ones as described by the synesthetes with colored hearing. The ones on the right had the colors altered or the orientation altered. So in this room where most people don't have colored hearing, the colors and movement associated to pitches of synesthetes have aesthetic appeal. And maybe that's because those connections between the between the auditory cortex and the visual cortex still exist in all of our brains. Maybe. Okay, so here are the data from Jamie Ward's experiment. So these are the data from the non-synesthetes. It's the proportion who liked the correct color, the one originally chosen by the synesthetes, as opposed to the opposite color. Dotted line goes up at 50-50. And most people like the correct color. And here are the data for the correct orientation, where the vote was more overwhelming in this room too, that most of you liked the correct orientation, and far fewer of you liked the changed orientation. So, what's the appeal of art, of music, by people with synesthesia? We don't know yet. But perhaps the persistence of some of the same connections in the brains of all of us influence how we listen to that music and how we view that visual art. If you've acquired a taste for synesthesia tonight, I welcome you to come to the conference for the rest of the weekend, which starts tomorrow morning with a keynote address by Jamie Ward, who did the research I just described on aesthetic preferences. Stay on for the banquet tomorrow evening, where you'll get a chance to hear the compositions of Sean Day, another individual with colored hearing who will be playing his own piano music. And sometime in the next few months, be sure to go to the McMaster Museum of Art, where there's a display of artworks by known synesthetes whose visual art is inspired by their synesthesia, including original works by Carol Steen, including the work that's on the cover of the program. In addition, there are works by some people who might have been synesthetic, like Tom Thompson and Van Gogh. The exhibition has just today been extended till December the 20th. The opening's tomorrow night. If you come tomorrow night, there's also a reception and a chance to talk to some of the artists. I'd like to thank the McMaster Institute for Music of the Mind and the American Synesthesia Association for making tonight's event possible. I want to remind you that there's a reception following the evening. Please come and have a glass of wine and some food with us and with the musicians. And we're going to end tonight with two pieces by Franz Liszt. Here's another quote. "That is deep violet, please. Depend on it, not so rose. The pitches had to be darker for that particular piece of music." Let's end the formal part of the evening by listening to Brett Kingsbury play two pieces, first Nuage Gris, and then Variations über ein Motiv von Bach. Brett?